Okay, so thank you very much for again for this new week. Okay, as it has been a while ago, I want to remind a few things I said last time, and in order to do so, I draw an example, so slightly bigger than last time. Last time I did A3. Now I did D4 for several reasons, which will become clear later. But okay, first of all, some people told me that they were bored by A-type. So I decided to do that it would be good to have at least one example which is not in type A during this week. So I took the smallest one, which is not in type A. Sorry, yeah, I think my microphone is okay now. So as I explained to you last week, there is something called the Auslander-Reiten quiver, and it has been used again yesterday in another context, and I will probably speak about it a bit more later, but now I'm speaking really about the representation of the quiver, or equivalently, as you know now, the module of a path algebra, but let's consider them as the representation of quiver at this point. So what is depicted here? So they are basically bases of the space of irreducible maps, as I explained to you last time. And in orange, in this case, I put the Auslander-Reiten translation. And usually reading the Auslander-Reiten sequence, as I told you on this graph, is not that difficult because you know that the Auslander-Reiten sequence finishing somewhere, the map which is surjecting there is the sum of all the arrows which appear pointing toward here. So if I want to know which AR sequence finish here, I know that I need to sum up all these things. So I will have the direct sum of these three in the middle. And then I need to compute the kernel. It's not that difficult. The kernel is here in this case. Okay? And then what we observed last time, that by starting with an initial seed, the corresponding cluster algebra, and doing what I called last time lazy mutation, but which is more properly called the freeze. So what was the lazy mutation? It consisted to say, okay, first of all, I don't want to mutate when there are composition of arrows because the formula is too complicated and I forgot it. So I decided to mutate only at so-called sink and sources. So I mutate here only. And additionally, as I don't want to write too much thing, each time that I can, I keep the old part of the quiver that I had. So if I mutate in X4, what does happen? I need to reverse all these arrows, but instead of redrawing the whole quiver, I keep the common part here and I just write the new arrow, and I continue like that. Okay, and I will obtain that. And what I told you last time is that there is a kind of obvious graphical coincidence between these two things, which can be made even more than a coincidence about that, because you can see that the denominator vector corresponds to the dimension vectors here. So Bernard reminded that yesterday. And actually, as you saw yesterday, but I will not speak about that immediately, you could actually complete the picture here by the so-called cluster category. And if you use the cluster category, of course, it will close here, because at the level of mutation, it's what it does, right? You went back here to the initial seed, so you will kind of close your picture. So, right. But at this point, I want to stay here. What else I wanted to say? I wanted to do another few comments about the quiver that I didn't have time to do. So there are a few easy observations, but which can be nice for you to know. First of all, okay, I will say something which is almost true, which is true in this case. If you want to know the map in between two objects or two representations in this case, this consists of linear combination of passes. So why I say it's almost true, because it's in the infinite case it's not true. So remember, maybe just a kind of side comment, remember the example that Pierre-Guy draw last, it was much better drawn, but like it looked like that, more or less. Okay, if you have an infinite case, what I just said is not true because you have some morphism going from here to here, and you cannot actually interpret them as paths because there is no path going from there to there. But in finite case, you also have this property, which worth noticing. Another property that I didn't say, but which is almost immediate, if you are used to that, is that all the maps here are either surjective or injective. So why that? Actually, you know all why that, because if I take two modules, or two representations, does not matter, and I take a map, you can always factor it through its image, right? So, of course, this thing cannot be irreducible, except if it's one of these two, right? So, yeah, it's not possible to have irreducible map which are not injective or surjective because we are in an abelian category and you have images in abelian category, as I told you, not last time, but the previous time. Okay, so we have this picture, and what is the aim of this talk is to understand by something called the Caldero-Chapoton formula, actually how to go from here to there. So what is the procedure which permits you, if you know a representation, to know this thing? So we know a part of the story because we already observed, we know, we didn't prove, I didn't prove anything at this point, but know already that the denominator is the dimension vector, so this is something I told you, and it seems correct, at least on the example. Pay attention that we are in type D4, I will say more about more general thing later, but at least in type D4 or A3 it works. And actually I can tell you that it works in any finite type. But now the numerator seems much more complicated. So yeah, if you expand it, there are a lot of terms. I wrote 1 plus x4 square or 1 plus x4 cube because I don't want to take too much space. Okay, so I will try to do my talk on this part on the blackboard, at least during a while. I would like to keep this piece of art during a while, because I will not redraw it. Okay, so first of all, I will restrict a bit. Sorry. Today, I will take k equals c. And then I will give you directly the formula, and I will compute an example with you. So. Oh, maybe I didn't put a title. Maybe I should put a title. Caldero-Chapoton formula. Okay, also called, in more general setting, cluster character. So the formula. So the formula is the following. If M is a representation of our quiver, we do the following thing. I define xm to be the following thing, and I will copy because I don't want to do any mistake at this point. I do the sum over all possible dimension vectors. So dimension vector are parameterized like that, and to be completely sure that I'm not losing anybody, I'm using this convention. So please remember. Okay, so 0 is a natural number, for today at least. And I take something that I will define later. And then I multiply by, so this is a number. This is a coefficient that I will explain you later. And now I multiply by a certain monomial that I will copy in order to be sure not to do any mistake. E, sorry. Something that I will call delta I. I'm not sure if you like this notation. I'm not sure either if I like it, but I decided to use that for today. This is just one of the this vector, and then delta I, dimension of M minus E. Dimension of M means dimension vector. Okay, so this is the formula. So of course there are plenty of terms that you don't know and that I will explain. This will be essentially what I will spend my time on today. So Chi is the Euler characteristic. I will speak more about it. And for those who are more geometer and who wonder which one, I mean, okay, we are over C, so it's well behaved. Most of things that you know, you can take just the Euler characteristic with coefficient in C. If it's not C, you can do some more fancy thing, but I'm not so aware of them, like using étale cohomology, and I will not speak about that. So we take Chi, the Euler characteristic, and we take some word you already heard about. I need to read it a bit. The Gr-E-M is the Grassmannian of submodules, sub-representation, sorry. When I say module or representation, it's the same for today, okay? Sub-representation of M of dimension vector E. So in the same way that the Grassmannian that was defined the other day was parameterizing subspace of a certain dimension of a vector space, this one parameterizes sub-representation of M of a certain dimension vector. I will construct it later, don't worry. And this thing is the Euler form. So, Euler form. So what is the Euler form? I will just write it. It's a bilinear form. So if I take two vectors, D and E, so these vectors are parameterized by the vertices of my quiver. So I never number the vertices of my quiver. You can number them if you want, but it's not necessary for computing. So you just take the sum at each vertices of the product minus the sum for each arrow. So an arrow which goes, for example, from I to J. And then here I need to remember the good order in order to not do mistake, of di ej. So it's a bilinear form. Yeah, this is in Q1. Yeah, I didn't say, but from the beginning, Q is a quiver, it's fixed as before. Okay. So we do that. And now the point is that this formula should be the formula which associates to M the corresponding cluster variable. So in order to make it more clear, maybe, I hope, I will do an example. So before doing an example, I will give a kind of vague idea that the thing, this number counts, and I put quotation mark, counts the number, or count the sub-representation of M of dimension vector E. Okay? So, yeah, you will see that you need to adapt a bit, but the essential idea is here. So let's do an example. Example. Right. I should not. Okay, sorry. Or maybe I start here. Example. I take this quiver, and for today I will try to stick on that quiver over there. Okay, so the quiver over there is the quiver for today. I take the following representation. So K, K, K0. Another point is that I only draw the dimension vectors, but they are all indecomposable. Sorry, I remind you that by the Gabriel theorem that we saw yesterday and last week, the dimension vector is enough to determine a unique indecomposable representation. For most of them, you can guess it easily. For this one, if you are used to do a bit projective geometry, you know that putting 3 lines in a 2-dimensional space gives some kind of unique situation up to isomorphism as long as you put the 3 lines in generic positions. So I let you think about it. You should, yeah. I let you think about it. Okay, now I'm taking this one, and when I just write arrows like that, it means that this is the identity to simplify. Okay, so how to compute this thing? I need to do a sum over all these things, which is difficult. However, this thing is counting some sub-representation of M, so yeah, any meaning that you can think about it, if there are no sub-representation of M of a certain dimension vector, this is 0. So I need to restrict on dimension vectors, which actually are dimension vector of sub-representation of this, and there are not so many. Okay? So what are the possible sub-representation of M? Okay, there are actually not that many. There are 5 of them, if I didn't miscompute. So there is 0 itself. I mean, the 0 means 0 everywhere, which is always a sub-representation of anything. What next? So there is a general thing you always need to start at tip of a row. A sub-representation needs to be kind of transitive via the rows. It's stabilized by the action of a row. So the next one in terms of size will be the one supported, the simple, supported at the middle point. Okay? We have that. Okay, so any other sub-representation will contain that. So now you need to wonder if you can add that or that. And actually you can add them independently. So you have this one. Okay, I put a row everywhere. Then you have also this one. And then obviously you have a 5th one, which is M itself. Okay, we'll just write M. Okay, maybe I'll write it here. Okay, M is a sub-representation of itself. And that's all. You have only these 5 sub-representations. So this formula will kind of be simplified. You have 5 possibilities for E, which are the dimension vectors of this thing. So I will do them one by one, and for each of them, I will try to compute this thing. So let's start by the easy one. Is take E equal 0, the 0-dimension vector, which is the dimension vector of this thing. So what should I obtain according to this formula? This chi, but actually there is exactly one such sub-representation. Think about it, you have no choice. If you want a sub-representation of this as a sub-representation of that, there is only one way to realize it. So I count them, and in this case there is one, so let's just make the assumption that this count well finite number, so there is one. Then I need to do this product, so it's a certain monomial, it's of course the thing which will be a bit annoying. So it's a product for I in Q0. Oh, it didn't start. Now I don't know, how much time ago did I start? Okay. Okay. Sorry. Right. So now I need this monomial. And what is this monomial? So I have minus E delta I. And of course, it will be, E is 0. Sorry for that. So I just have this term, which remain. So it's delta I, comma, dim M. Okay, and dim m, I know that it's, what is dim m is delta 2 plus delta 3 plus delta 4, right? Okay, so here, maybe I draw a table for you of the scalar product of this Euler form. So suppose that we have E here and, okay, maybe D like that. I will just draw a table for you, and then it's bilinear, so I just need to understand what it does here. And it's actually not so complicated, so I will just draw it very fast. So how to compute d scalar E? Right, so d scalar E, there is a first term, which is this term, and of course, it's one on the diagonal, this term. Okay, so I just write one on the diagonal. And then the second term is one when there is an arrow between D and E. So yeah, it will be, so which, okay. So it just means that there are arrows from everywhere to vertex 4, except from vector 4 to vertex 4. And there are zeros everywhere else. Okay, using that and using basic things that you all know, you can compute that this is equal to, so I hope I didn't do mistake, but priori I checked. It's x1, x4 to the minus 1. So, I mean, let's do it really for this one. I will not do it for anybody else, but here the second term is delta 2 plus delta 3 plus delta 4, so you are summing these three columns. And if you sum these three columns, these two columns cancel out. Then you have this one, which stays with a minus 1, but you have a minus here, so x1 appears with a positive sign. And if you sum these three columns here, you also have delta 4, which appear, you have the fourth coordinate, which appear with a 1, and as you have your minus, you have x4 to the minus 1. Okay, I guess that you got the point, I hope. Okay, so now I will write fast the other one. So I'm sorry, I will not take the time to detail the thing. So here you find, this is a good exercise, try to do it by yourself. X2 to the minus 1, x3 to the minus 1, x4 to the minus 1. So E equal delta 4 correspond to this representation. So which one I have? E equal delta 2 plus delta 4, right? Oh no, I did delta 3 plus delta 4 before, sorry. So delta 3 plus delta 4. So what do I obtain when I do delta 3 plus delta 4? I obtain x2 minus 1, x3 minus 1. Then E equal delta 2 plus delta 4. And right, what do I do when I go from here to here? I just exchange the rule of 2 and 3, and as everything else is symmetric with respect to 2 and 3, I just exchange these two things. So actually, I obtain the same thing once again. And then the last one is E equal delta 2 plus delta 3 plus delta 4. And I obtain x2 minus 1, x3 minus 1, x4. So I have these these 5 terms. I sum them up. And then, okay, let's do it. So maybe I write it here. What do I obtain? I obtain xm equal x1, x4 to the minus 1 plus x2. Okay, maybe I put to the same denominator at once. I mean, so what is the biggest possible denominator is this one, all right? It's x2, x3, x4. So here, what do I have at the numerator? I have x1, x2, x3. Here, what do I have? I have 1. Here, so I have twice the same term. It's 2x4. And here, so I have x2, x3 in the denominator, and I have x4, so I have x4 squared in the numerator. I hope that my things are clear. However, the only thing I want to make you notice is that if you go back to this big diagram, the representation I took is here. So normally, the variable I wrote is there. Is this true? Please check. It seems to be true, right? This equals that over there. Okay, so you. So what? The Euler form, you mean? Yeah. Yeah. -1 each. Yeah, I mean, these two things give the same Laurent monomial because you have a, I mean, this is a situation which is symmetric with respect to the transposition to 3. Okay? So this is symmetric with respect to the transposition to 3. This also, therefore, I expect the same monomial. Okay, just please check that. Yeah. And it makes these two appear here. Is it clear? Okay. So, yeah. And as I find a good result, I'm quite confident about computation. Okay. I should tell you, you can train to compute this freeze. It's not that easy to compute the freeze over there. You need to simplify a lot of polynomials. However, I did it the brutal way. I really computed it in order to check that I actually finish here. So this value should be quite solid, because otherwise I would not have succeeded to come back on the initial seed. Very unlikely if I do a miscomputation that I compensate it just after, normally. Okay? Okay, I erase that because it's not so interesting. So now I will try to enter more in detail to explain you each of the terms that I'm using. So Grassmannian. So Grassmannian, you already heard the term in the talk of Metri. So C last week. However, I will remind slightly the basic things I need about Grassmannian. So first of all, I give an exercise. So this exercise, the idea is that if you want to understand how to construct the Grassmannian, please do the exercise. If you don't care, please don't do the exercise. Okay, this is the idea. So how do I construct the Grassmannian? I'm speaking about the Grassmannian last week. So first of all, you observe that there is a one-to-one correspondence of the following way. So I will JLK. So you take matrices. I don't know how to write matrices. Sometimes I write like that. I hope that you like it. So you take all full-rank matrices with n columns and with k rows. They span a vector space. So of course, it permits you to go to the Grassmannian at least pointwise. Then you make GLK act on it to the left, which means that essentially you are considering your basis up to a change of basis, which is reasonable because actually what you want to know are vector subspaces. They are not basis, right? So you make this thing. Second point, you did what was done last week. You construct an injection like that. So So this is that I prefer to write it like that. So I hope my notation are the usual one. I think so. So I prefer to write it like that because I want the good exponent. And if you take some x here, where do you map it? This is easy, or this is easy. Okay. Okay. This I want to include this thing. Okay, I repeat that here. I want to include it here, and what do? If I take a matrix X, I map it to the family of minors, of maximal minors. So I is just a subset of 1 up to n of cardinal k. So this thing is really that. Nothing but that is n choose k. Right? It's a subset of a set. And then this is the notation of Macquarie of last week. It's just the minor with the column parameterized by I, and full rank, it takes all the space. And of course, the fact that you start with full rank matrices make that this thing actually does not reach 0. You have at least one of the minor which is non-zero. Another thing is that what is the action of GLK? Think about it, but action of GLK multiply all the minor by the same constant. Because when you multiply a matrix by an element of GL, you multiply by the determinant of this element. Therefore, my target is well defined just up to a scalar, so that's why I need the projectivization. So please check that. The injectivity is not that difficult to check. It's a bit tricky, but I let it as an exercise. Just do it. And 3, image. No, actually, the injectivity is easy. Sorry, it's not what I wanted to say. Image of phi is equal to the. So I take the small delta I is just an abstractization of the big delta I, satisfying Plucker relation that you learned last week. And what is actually slightly tricky, but not that difficult. So there is one thing which is easy that you can do all easily, is to check that actually this thing satisfies the Plucker relation. So check it for n equal 2. So this is the basic case. And for the other one, you do column expansion with respect to the common indices of your Plucker relation. I let you do that by yourself. It's really an exercise. What is the point, which is slightly more complicated, is the surjectivity. But actually, you have some kind of strategy to deal with that. The trick is to suppose that one of the is non-zero because you know that. Then you focalize on this minor. You change it to the identity by multiplying by an element here. Because if some matrix is invertible, you can. So there are one of the submatrix which you can change by identity. And then you can realize that once you know that there is identity somewhere and you know all the delta I, you can reconstitute all your coefficients by essentially taking some minor, which are almost your identity matrix, except one column. And you change each column of your identity matrix, which have been fixed by other things. Okay, sorry, it's too fast, but yeah, if somebody has questions how to do that, please ask me later. You can all do it. Okay, why is it interesting to see that? Because actually it implies that this thing is a so-called projective variety. Right? It's a subvariety of a projective space defined by homogeneous polynomial equation. And when I say that, of course, there is a kind of exaggeration. What I mean is that I identify this thing with the image of that thing, okay? Obviously, if I define it point-wise, I need to add the structure, and this is the way to add it. Okay, so I have this exercise, and the fourth question in the exercise that I just think I need to add, well, it's trivial, but I will add it anyway. A change of basis in DLN. So if you change now not the basis of the small space, but the whole space, acts on GR NK by an automorphism of variety. So why do I add that? Because now I have an abstract version of Grassmannian, and GRK of V, if V is a vector space, is well defined. Okay, this is. So what means GRK of V? It means the K subspace of V, but now I didn't fix a basis. That's the only difference. I want to have an abstract version where I don't need to fix a basis. Okay, so now I have Grassmannians, but I want a bit more about Grassmannian, but you will see it's not that difficult. So now I start to be in the situation where I need to keep most of the thing in the blackboard. So now I need another version of Grassmannian. I need Grassmannian of sub-representation of a given representation. So how do I do that? So if I take a representation of the quiver and a dimension vector, I want to define some Grassmannian of submodule of M of a fixed dimension. Actually, they're not that difficult. What is the condition to be a submodule of a given module? It's essentially that at vertex y, sub-vector spaces, so that I can start to write. It means that I take some, okay, maybe let's call it V index I for I in Q0, which is, for each of them, in the Grassmannian of dimension EI of MI. Okay? So I just take one subspace for each. But of course, this is not a sub-representation. It's just a collection of subspaces. So what is the condition? Is that actually each VI is mapped to Vj by each time you have an arrow. So for all Q of the form Ij in Q1, so in the arrow space or in the set of arrow, you need that, so what I denoted by MQ of Vi should be included in Vj. Okay? So this obviously parameterized sub-representation, think about it. It obviously is parameterized sub-representation of a representation. The question is, what is that? Is it still a variety? The answer is yes. The point, and this is a general point, you can also do that as an exercise. It's very interesting, not that difficult, but very interesting. The point is this is a closed equation. So you remember, okay, maybe I didn't remind Zariski topology, but you remember that Zariski topology is defined essentially as closed as zeros of ideal of polynomials on the variety. So you need to see that this is a polynomial equation. So there are plenty, this is what is nice about Grassmannian, there are plenty of natural things about subspaces which turn to be closed or algebraic or which have good behavior with respect to the structure of variety. So this variety is very well behaved with respect, for example, to intersection of subspaces or with respect to all natural operation you want to do on subspaces of vector spaces. Especially this is a closed equation. So let me tell you in 1 second why it's a closed equation. So you need to go back to MKN. So you have two bases. One basis of one space and one basis of another space, and you want to control when they are included in each other. How do you do that? You put your two bases one above the other, and the rank of this matrix should be the dimension of the big space, right? If you want a small space to be included in a big one, when you put the two bases at the same time, all the vector of the small basis should be redundant with the vector of the big basis. Therefore, it's a question of rank of this matrix, and you know all how to compute that with determinants, which are polynomial equations. Okay. So now we have a notion of Grassmannian sub-representation. So we have a next step. Okay, now what did I want to say more? Okay, so this I will skip because I already said early. Okay. Of course, yeah, maybe one point. When you take a point here, you can also give it naturally a structure of representation of Q just by inducing. This is a sub-representation, so you identify points with certain representation. Okay, well, it's not in detail. Okay, now next term I need to define here is this term. So what about the Euler characteristic? So I know that there are a lot of characteristics. There are a lot of geometry in the room, and they will be not so pleased by my introduction. I'm sorry about it. Because I have no time to do a proper introduction about that. So I will use Euler characteristic as a kind of black box. So I will somehow call Euler characteristic some thing which, for a certain variety, give a number satisfying a certain number of properties that I will list. And a theorem from algebraic geometry is that this Euler characteristic actually exists. I will not prove that. I just assume that it exists, and it has the following property. So first property, the Euler characteristic of the empty variety is 0. So when you count something which is empty, that's why I call that counting, this is 0. Thing. Second point, if you count C to the n, I write it like that. It's what Metreyev wrote, AN, I mean the affine space, affine variety. This is just one. What else do I need? I need the following thing. So this is true for any n. Maybe I should write it. Including 0, so it's true also for a point. Pay attention, this is not a vector space. It can be shifted. It's really a variety. But I write it like that for convenience. So 3, the Euler characteristic of V, and I did not define on which set it's, so I will be slightly more clear in 1 second, is equal to the Euler characteristic of X plus the Euler characteristic of V minus X whenever X is constructible, and I will tell you what it means, constructible in V. So what means constructible? It means finite union of locally closed. And I should say Zariski locally closed. Each time I use some topology vocabulary, it's for topology of Zariski locally closed. Maybe it's almost an anecdote, but why is it called constructible? It's because it's exactly the smallest set of subset of V, which contain open subset, which is stable by union, stable by intersection, and stable by complement. So infinite step. So you can kind of construct all these things just by iterating this thing. So this is the reason it's called constructible. And why this notion is important, and this is one of the reasons is a so-called Chevalier theorem, that if you have a morphism of variety, if you have an algebraic map, then the image is automatically constructible. So constructible is some kind of what you want to consider somehow as subvariety. Okay, like you want to at least have that in your toolbox to be able to do things. So what it means is that each time that V is the union of two constructible things, because of course, according to what I just said, if X is constructible, V minus X also, then you can compute the Euler characteristic just by splitting like that. Then the last one, or, okay, yeah, a last one. So if you have an algebraic map, so F is an algebraic map from X to Y, so these are two varieties. So I remind you that algebraic map, I will not define, but okay, in all algebraic varieties, you have some notion of polynomial, either local, either global, depending on your context. An algebraic map are a map which kind of are polynomials. Okay, I use quotation mark because you need to pay attention, but they are essentially locally polynomial map. So if F is algebraic, and each time I need an algebraic map, I will admit that it's algebraic. I will not have time to prove anyway. So each time that F is algebraic, and the Euler characteristic of the fiber is constant, so this is the fiber, the converse image of Y. So you can prove that it's constructible, so it makes sense to compute the Euler characteristic. So each time that it is constant over the whole Y, then the Euler characteristic of X is C times the Euler characteristic of Y. It's a bit tricky to prove, but okay, the picture I like to do about that is the following one. You have your variety here, you have your X here, you have your Y here, you have some of them like that, and then you have somehow, I would say, even if it's not completely true, it's a bit more general, you have kind of constant fiber. Then the size of this is the product of the size of this times the size of the fiber. Okay? So Euler characteristic is kind of a size, it measures size. Also for union, it seems to measure size. Okay, so, okay, and the corollary of that, maybe I put phi, which is a consequence of 4. Yeah. Sorry. Yeah, okay. Essentially yes, but I will have a very restrictive definition of variety to be sure that I'm not telling you things wrong. At least in this context, yes. Any subvariety of the Grassmannian, for sure. Any nice variety. I don't want to ensure you that there are no kind of geometric things that I don't understand in one corner. Okay. Say that if you take a projective variety or something like that, it works. After quasi-projective as well. Yeah. This, what I was saying here, this is a closed equation. So it's closed in a projective variety, therefore projective. This is a product of projective variety, and then you take a closed. So, yeah, sure. It's the usual Grassmannian. The only thing I want is to forget about basis. So it means please choose a basis and take the usual one. However, what I told you in the last question of this exercise is somehow when you change a basis, it canonically change. So yeah, you can forget about the basis essentially. Okay. So now we have that, and 5 that I will write it like that because it's kind of obvious. The Euler characteristic of a product is the product of the Euler characteristic. It's obvious modulo the fact that you should pay attention what is the product of variety, but I will not speak about it now. But it's obvious because whichever the good notion of product is, you have a projection from the product to one of the components, because it's a categorical product in the good category, for example. Therefore, you just apply for this projection, which is algebraic. Okay, so you have that, and somehow, with this toolbox, you can compute Euler characteristics of nice things, constructible I mean, like reasonably easily. I will give you an example, which will be kind of important for us in this context. So let me go to my next page. Proposition, and I will give you the proof fast, because I feel otherwise I will start to have problem of time. No, it's still okay. If I take the Euler characteristic of JR and K is just n choose K. Okay, how to prove that? You just use this axiom. So let's just use this axiom. When I say axiom, I'm lying. I mean, it's not axiom, it's a property of something which actually exists. But I kind of see them as axioms for now because I didn't construct it. Okay, so how to prove that? You do naive things. So you fix a certain subspace C to the n minus 1 of Cn. And then you say, okay, I want to study k-dimensional vector spaces of that. Either they are included here or not. Okay, so what should I do? I should, okay, first of all, we have this inclusion. GR n minus 1 k is included in GR and k. Just following this inclusion, if you have a subspace here, you have also a subspace here in an obvious way. And of course, everything that I write as an inclusion is an algebraic inclusion for obvious reasons that you don't know, but think about it. So we have that. And then what happened where I try to understand the complement of that. GR and K minus GR n minus 1 K. So now I have something which is the complement, and I want to sum up the two Euler characteristics of that. I claim that I have a map from here to something else, which is GR n minus 1, K minus 1. And this one is very easy. It just maps a certain subspace, how should I call it? Maybe V, to V intersected with Cn minus 1. And pay attention, this is really this Cn minus 1. Maybe I should give it a name, more reasonable name, but each time I say C to the n minus 1 is this one. So I have that. So now I want to understand the fiber of this thing in order to apply for. What is the fiber of that? I will draw some picture, which I'm very bad at, but we will try at least. So I have Cn, which is here. Okay. No, this is Cn minus 1, sorry. Cn is everything. It's a 3D dimensional space, and Cn minus 1 is a 2-dimensional space. Okay? So you have that. Then now, I map V to its intersection with here. So I took a V which is not included. So my V look like, okay, I will draw my V. My V look like, I don't know, something like that. Okay, sorry. I hope that CV, it's another subspace. And V intersected with that is just this line, right? This is this. This is the intersection. Now, what is the fiber? The fiber above this point is the thing which parameterizes all the yellow things which have the same intersection. And I affirm you, and it's not so difficult, that if you take a line which is generic enough, here, the yellow space, once you know the intersection, is parameterized by this line. You all see that, right? This is the intersection. I mean, I take the intersection here. Of course, knowing the intersection and that, I know the hyperplane. Therefore, the fiber of that is the red line. And the red line has Euler characteristic 1. So it's, pay attention, it has an affine space. It's, the red line is not going through 0, but I don't care about that. So I know the Euler characteristic. Pay attention, you could imagine almost, and it's actually not true, that I could map this to a product of that with C. But actually I cannot, because I need to change the red line depending on the choice of this yellow line. When I choose the yellow line, I can choose the red line. However, if I choose the red line a priori, yellow lines that are parallel to red line will make a problem. Okay, so I have this fiber, but therefore, using 4, it means that Euler characteristic of GR nk minus GR n minus 1 k is just equal to the Euler characteristic of this thing. Right? Therefore, so this is because I use that and I use the fiber as constant Euler characteristic 1. Therefore, the Euler characteristic of GR is just the sum of the Euler characteristic of GR n minus 1 k. Sorry, I put the parenthesis in a strange way. Plus the Euler characteristic of the Grassmannian n minus 1 k minus 1. And here you recognize all the induction formula defining choose k. And you just need to check that if n equals k, there is only 1 point, therefore it's Euler characteristic 1. And if k equals 0, there is also only 1 point. Then, yeah, it satisfies a good induction relation. So, yeah, okay, let's finish the proof. Okay, so you see that already with just these few axioms, you can kind of compute some Euler characteristic if you play correctly. Okay, so now we know how to compute Euler characteristic. I want to tell you one more example about that, because I told you before that I need to count kind of the sub-representation of vector, dimension vector. So is it actually as simple as it seems? We'll show you that no, and I will tell you why. Let's consider a very special case, which is somehow the biggest possible example. Maybe I let that here for one. No, I will not let it here because I will not need it today. So, okay, yeah. Okay, so example, let's take the same quiver as before, and let's take the following representation, the one which is here, the one which is the most annoying, because this is the biggest. So let's take this representation. So it's k square, k. And to be precise, you need to put this line in general position. So one possibility is to put 1, 0, 0, 1, and whatever you want, which is not one of them. Yeah. And they are all isomorphic with each other as long as these three things are not are generic enough. So you have this, this thing, and the question is, what is the Euler characteristic? One of these coefficients will be the Euler characteristic of dimension what I call delta 4 before, so concentrated here, of M. And then, what is this thing? Let's think about it. How many what are the sub-representations of this module of dimension 1? Well, you see that you have only a row going in. Therefore, you have no way to have constraint about it. You can take any line here. They are all in what we call the circle. That means that they are not inducing constraint. Therefore, you can take any line here. Therefore, you just have a P1. So you choose a line in this. Yeah, I said k equals CE today, so k equals C. Or it does not matter, actually, but let's say k equals C. So you have this. And how to use it? Okay, you know that the P1 is Greux. You need to put k equal 1 because you are parametrizing line. Therefore, it's 2 choose 1. I mean, okay, this one is a bit confusing. So 2 actually, so you have 2 choose 1, so this is 2. And then you see that you actually need a bit geometry for this formula. When I was saying you count, it's not true. I mean, you cannot count the size of a P1 point by point. You need some kind of measure. Okay, so chi is what is our measure somehow. You need to measure the size of a space. Okay, so pay attention, it's not a true measure. It's not positive, for example. If you take P1 and you remove 3 points, the Euler characteristic becomes -1, so it's not really a measure. But we use it as a measure. Okay, so you have this. So it gives you an example where you have a 2 appearing here, but this 2 would not come from 2 points, it would come from some complicated variety. Okay? Okay, I still have 15 minutes. I will say a bit thing about Euler characteristic, Euler form. So Euler form is something that I defined here, but I want to give an alternative definition which is very easy, or very easy. Which is more handy from a representation theoretical point of view. So Euler form. So I will call that maybe proposition or lemma. No, it's lemma. It's not a proposition. It's lemma. Lemma, but important lemma in a certain sense. If M and N are 2 representations of Q, then the Euler form of their dimension is just the dimension of the home space minus the dimension of the X1 space. Okay. I'm saying this is easy, so I will give you a fast argument. So how to prove that? Start by doing it on simple. So I remind you that simple module or simple representation means representation which are concentrated in one vertex and dimension 1, right? So these are the simple. So do it for dimension of M equal dimension of N equal 1. So when I don't underline, it means the total dimension. You add up all the dimensions. So what would happen? There are not so many choices. If you think about it, either you are taking the same simple, then there is an isomorphism, but you cannot construct short exact sequence which don't split. It's easy, please check. So in this case, you will obtain 1 and 0. And then you see that it coincides with that. And then if you take different one, well, obviously, you have no morphism from one to the other because there are different vertices. However, there can be extension, and how you will see if there are extension, you will see if there are arrows. The way to construct an extension between 2 simple, which is non-zero in the extension group, is something like that. So you take what I will call Si, which is a simple at vertex I. Then you will do something like that. So you will take K at vertex J, and K at vertex I, and you will put the identity here, and then you will put Sj. So this is typical short exact sequence, which is not split. But to have it, you need an arrow. So it's a bit the example I gave you in an exercise once. I asked you to compute the extension between S1 and S2 over A2. It was the first exercise. This is the same thing. Therefore, essentially, to count this term, you need to count arrows, which is what this term does. Okay? And then, after what do? You use long exact sequence. What happens if M or N is bigger? So this is a general thing. You always have a simple module which injects in it. So suppose that dimension of M is bigger than 1. And there exists a simple which goes inside M Si inside M. And then you can quotient it like that. You have a short exact sequence. How do you do that? You have plenty of ways to do it, but on a quiver, it's relatively easy. You start at a non-zero vertex. A vertex with a vector space is non-zero. And each time you see an arrow which permits you to go somewhere which is non-zero, you continue. At some point, you stop the process because there are no infinite length paths. Therefore, you will end up at some body which is a submodule. OK. And then you use a long exact sequence. So long exact sequence. So remember what they were. I don't know if really I have time, but yeah, I will do it. OK, I did it for M, so we'll do the difficult long exact sequence. The long exact sequence was like that. You have 0 ohm M over Si. No, not Si, N. I don't move my N. Then home M, M Si. Then home, no, this is not Si, it's N, sorry. Then home Si N. Then the same thing with X1. And my yellow last row that I will put in yellow again. And what's the point about this is that once you have that, this is a very easy linear algebra lemma that the alternate dimension, the sum of the alternate dimension of all the terms is 0. But it tells you exactly that, OK, if you take this formula, OK, let's call that for a while prime form. It tells you immediately that basically this is additive, that M n prime is equal to M Si n prime plus M over Si n prime. Okay? Therefore, you can do an induction if M is bigger than 1, and if N is bigger than 1, a dimension N is bigger than 1, you can do the same induction with the other long exact sequence, and that's cool. Pay attention, this thing is important. What I wrote needs to be adapted if you are not over a quiver, because I told you that if you are not over a quiver, you have not this arrow here, so it needs to be adapted. And maybe Pierre-Guy will speak about it. I don't know, or he told me he did not know yet either. So, yeah, sometimes you need something more complicated. But for us, it's fine with like that. OK, so I told you that. And now I can go to somehow the main theorem. So what is the main theorem? Or the main theorem, no, kind of the key point of the main theorem that I will not prove today by lack of time, but I plan to prove Friday. So theorem, which is due to Caldero and Chapoton. So this is a theorem that has an history. So Caldero-Chapoton is the first version. Caldero-Keller, that I will not describe here, so it's generalized by, and maybe Pierre-Guy will speak about it, or I will maybe have a bit time Friday at the end, I don't know. And OK, it has even been generalized more by Jan Palu, maybe I will say. And probably in other contexts generalized in other ways. So, OK, I'm taking the historical version. So I will start by the historical one. So I take two representations. So which one? Okay, yeah, I will do 3 points. So for m, n representation, we have x m plus n, which is equal to xm xn. This is not the most difficult part. 2, for an AR sequence, Auslander-Reiten sequence, so of the form 0, tau m, n, m. Yeah, I'm sorry, I changed my convention with the previous talk. I was calling my representations x. However, I don't want to write xx. So that's why they became m and n today. Okay? So for n, we have x m x tau m equal xn plus 1. And 3. So, okay, now how do I want to write it? So for a projective, indecomposable projective. Or maybe before I write it, I say a small comment about AR, AR thing. So I want to give you a flavor of what I want to do. So look at this correspondence here. Each AR translation, or each AR sequence, corresponds to an exchange sequence. So you can guess already that what I wrote here is the exchange sequence, right? However, unfortunately, in this context, this is what also solves the cluster category, you don't have AR sequence starting or ending at projective. The same way you don't have AR sequence starting at active module. Therefore, you need somehow to artificially understand this part where you don't have the AR part. That's why you need some kind of AR sequence in the cluster category, or AR triangle, Auslander-Reiten triangle. So it's somehow what plays this thing. So you have X, so Pi, and I use the same notation as Pierre-Guy. So Pi is the unique indecomposable projective which is generated at vertex I. In other terms, Pi is the projective cover of the simple module at vertex I. This is the definition of Pi. So you saw example in Pierre-Guy's lecture yesterday. So you have that, and what I will say is that xi multiplied by, so xi is the initial variable, so the one which is not in the picture, upper picture, is equal to what? So I will say the product for pj, sorry, I copy because I want to, in AR. So you take all projective which have an arrow to the projective I in Pi, and you take xpj, multiply by the product for all arrow of the form Pi to Pj in AR. But here you don't put xpj, you put xj only. Plus 1. So it looks very much like this one, except that this term is a bit messy. Okay? So you have that. Okay. So I will prove a corollary, and that will be all for today. I will prove this. I think I'm close to ending my time anyway. So I will prove a corollary of this thing, which is the important corollary we spoke about. And next Friday, I will explain how to prove that, at least big line. And I hope that I will have a bit more time to explain you something else. So, right, I keep the formula here. Why not? It's actually more important than this for me now. Xm is here. So I remind, my strategy is I want to understand how to go from here to here. I define an Xm, and I want to prove actually that it works. And these formula are essentially the exchange formula that were defined by Jacob the other day. I will just explain, but you will see it's pretty straightforward now. Of course, if you admit the lemma, which is a difficult thing. But once you admit the lemma, as a corollary, you have the following thing. So corollary, there is a bijection, and I will do only this one. I think Bernard told it like that yesterday somehow, but I rephrase it. There is a bijection from the indecomposable Q module that I will write like that. It's an ad hoc notation. I don't know if I do. To the cluster variable, except the initial one. So the initial one is the xi. Okay, so I remove the xi, which is just given as it should. And I will add something, which, okay, this is not very rigorous, but I will write like that, respecting the freeze pattern. So I remind you that what I call a freeze is this picture. Right. And I will add a comment in 5 minutes, or 5 seconds, because I don't have 5 minutes. But I will add a comment soon. But how to prove that? It's actually easy to prove, and I will not even write the proof. You just... So what I showed you is that you can do this lazy mutation. So you can mutate only at sinks or source, and then you get this mutation formula. So what is the mutation formula here? It's always, for all this kind of very easy exchange sequence, is that times that equal the product of these three plus 1, always. But what do I read in the first one? I read that if I take here, I read that, when I say that, it may x that times that equal x of the direct sum of that plus 1. But the small one over there tell me that the x of the direct sum of that is actually x that times x that times x that. Therefore, at least for AR sequence, it works. Okay? Then, it's not quite finished, because actually I'm starting in a point where I already need to know something, because I don't have anything about here. However, for some kind of regularity of the diagram, and I will not enter in detail, 3 is exactly what gives you the mutation of the initial thing. So if you take xi here, the kind of virtual inverse Auslander-Reiten translate of xi is actually pi. So what it tells you is xi times pi is equal to some 1 plus something, and that you can read on the diagram. Check that it's a good monomial, but it's not difficult because it's essentially defined as it should be, up to the fact that you need to know that somehow this diagram repeats this one, and that there is it gives a bijection between xi and projective. So x4, p4, x1, p1, x2, p2, x3, p3. You need to know that it's indexed like that. But it's because I indexed my xi in such a way that it's like that. So my xi are chosen in such a way that this pattern is repeated in a compatible way. So it works. And now you know, what do you know? You don't know all. You know that this lazy mutation, all the variables that I can obtain by lazy mutation, come from object. Now you need to add, so if I do the proof, somehow, the proof are 2 parts, one easy, one difficult. I did the easy one, but the difficult one is to know Gabriel's theorem and the classification of cluster variable. This thing, up to the fact that you should know that all these things are distinct, I'm sorry I didn't tell it, you have the good number. Because Jacob told us that the number is a number of almost positive rule. Here you have the simple negative, so you have as many as you need. And something I should say, and I didn't say, so a last final remark. I'm sorry about it. Remark, you can rewrite the cluster character in the following way. It's not very useful for our purpose, but it's useful to understand something. It can be written in the following way. 1 over the product for I in Q0 of xi to the dimension of mi, or in other terms, the ith entry of the dimension vector, times the sum for E in Q0. Sorry, why I put Q0? Sorry, it's n to the Q0. Sorry about that. N to the Q0 of the Euler, so the same formula essentially. You have the same monomial times the product for I in Q0. And here I will copy because I don't want to do a mistake. I don't have time for that, but the sum for J, the arrows J2I in Q1, okay, right in Q1, of EJ, plus the sum for I to J still in Q1 of dimension MJ minus EJ. Okay, this is not difficult. Just plug everything here and use the formula here. And try to put as much as you can this term out, then, okay. Say that you will have one of the terms where these two things will compensate. This is this term. You put out this term and you keep only this term inside, and this term somehow is constant. Means that this term does not depend. When you add up the two things, the part which comes from the first term is constant, and this is the part here. So what's the point about that? The point actually is that modulo just a bit thinking, the denominator is here. Okay, these are positive exponents now. Here you have a denominator. So this is the denominator that I was expecting, right? So it's good. So you need to check that there is no simplification, but this is not that difficult. Okay, you need to think about what look like linking quiver and think about it. This is not so difficult to prove that in this specific case you cannot have simplification. Therefore, to think the dimension formula works, but also it's injective. That means that I cannot have twice the same because here I don't have twice the same dimension vector. Okay, thank you very much, and sorry for the time.
For that excellent talk. Any questions?
Yeah. No XPJ. Okay, very good. Look what it looks like. Okay, now this is very interesting. So suppose that I'm mutating, okay, it's a bad example actually because only one of them appears each time. But if I'm mutating here, this appears, which comes from PJ. If I'm mutating here, these appear. So depending, some xi in the exchange formula need small xi and some other need the xpi, depending the orientation of the arrow. So pay attention, the way I index the arrow is a bit funny. So the point that I make correspond this arrow to this arrow, first of all. I use this bijection, and then I use the exchange formula at this level. But then if you have an arrow coming from, so xi to somewhere, it will give an arrow coming from small xi to the small xi. However, if you have an arrow coming from somewhere to your pi, it will give an arrow coming from your small xi to a projective. So pay attention, both cases exist depending on the orientation of arrow. This is in turn twin. You need both xi's and pi's to do the mutation here. So yeah, no, this is not a typo. You have two cases which appear depending on which one you are and the direction of arrow. Which is the initial. The initial is associated to nobody. Then at this point, in the cluster category, it's associated to the shift of projectives, but in this case, it's associated to nobody. And projectives are here. And if you mutate some initial variable, you need initial variable or things coming from projective. You don't need to look further, but you need this part to be able to mutate all. Yeah. Okay, so I will explain a bit. I tried not to extend too much, but I will explain a bit. So suppose now that you have your cluster category as a whole. Okay, the one defined by Bernard yesterday. There are two possibilities. Either, so Bernard told you essentially, I don't know if it was stated like that, but clusters are maximal rigid objects, or something close cluster tilting, but here maximal rigid. And then the exchange diagram which corresponds to this, in good cases, is just a sub-quiver of the Euler, of this AR quiver. So let's think first about this case. So for example, if I take this, no, not this maximal rigid, this is the maximal rigid, then I have, in the cluster category, I have this functor om t blank that Bernard introduced, which go to the module category, of endomorphism ring, but it does not matter. This will give us, once you go here, an expansion formula of any cluster variable in terms of this initial seed, the first thing. Second point, you could take, but this not everybody knows yet, but I hope it will be clear by the end of the conference. You can take some maximal rigid which don't look like that, but then you still have an endomorphism ring which give you a quiver. Unfortunately, this quiver is not necessarily acyclic, but it follows a mutation that Jacob defined. You need to add composition of rows, and you have something which is not acyclic. That's life, and then the endomorphism ring has a relation because it's finite dimensional, but you can still do it. And in this case, you need to adapt a bit. And why you need to adapt? Because of the yellow arrow which disappears from the blackboard. Because, I mean, you need, in this case, I use strongly that the algebra is hereditary, therefore that I have this identification between the naive Euler, the two Euler form, there are essentially two versions of Euler form of the diagram and Euler form of the category. They coincide, but I need the yellow arrow at the end. If you don't have it, you have a possibility that maybe Fergie will speak about, but I'm not sure either. He's not sure either. Oh, but yeah, no, I mean, this is not exactly the trick. The trick is more along the line to invent a category where every object is of projective dimension 2. Okay, I reformulate for you because I know you know that. Sorry for others. You replace object by their presentation. And you play in the word of presentation, and then it works. Presentation is projective dimension 2 by definition. So, of course, here presentation equal resolution, so you don't need that. But yeah, the generalization is not by generalizing the Euler form, it's by truncating the resolution. Okay.
Any more questions? Okay, if no more questions, let's thank Laurent once again.